And by doing so, the flux of ice is actually increasing from the greenland ice sheet into the surrounding ocean. Recently, researchers who are now at Lamont, they did their work at Harvard, Johan Ekström, Meredith Nettles, leading the study, showed that if we are looking at earthquakes around the ice sheet, what we see is that there are earthquakes that are induced by the movement of ice, basically when the ice is sliding on the bedrock. And you can see here that most of these earthquakes happen around July and August, September. That's when it's warmest. If you then look how that evolved over time, and we are going from 93 to 2005, they measured about 136 earthquakes in 7 groups, indicated by these points. And they can distinguish the earthquakes that are triggered by ice movement from the earthquakes that are triggered by crustal movement. They have the means to do that. And you can see that there is quite an increase in the frequency of these earthquakes from about 5 to more than 30 between 93 and 2005. So what we can conclude from that is that the melt area over Greenland is increasing and the split of the ice seems to accelerate. Now, Wallace said that a lot of the model calculations indicate that it will take many centuries to melt Greenland away. But on the other hand, if we would manage to melt it away, it is 7 meters of sea level. So it is a major issue that we have to look at. And recent studies also indicate that the model projections might not have captured the nonlinearities of an ice sheet decay, and it might happen much faster than what we project from our model calculations. We go on land. We see similar changes. Here we see from 1960 to 1995, that's work by Womanowski at the International Arctic Research Center at Fairbanks. We see that permafrost is warming and that the upper layers here, 12 centimeters into the ground, is now at this site in Fairbanks, is basically thawed. And that the deeper layers here, about half a meter depth, 1 meter depth, are sort of coming out of the freeze state into the state where it's thawed. That has tremendous implications for the groundwater flow, because we are forming groundwater flow systems that simply could not be there in a frozen state. And projections by the Arctic Climate Impact Assessment indicate that the permafrost boundary will move from this line here up to here, and from this line here up to here. So we will basically decrease significantly the area that's covered by permafrost. We have changes in vegetation. What is plotted here is the number of trees that show rapid growth and germination, and it's sort of, if you look at the time scale here, 1930, 40, 50, 60, year 2000, in recent years there is quite a bit of movement of tree zones further north. And that is also indicated in this, in the comparison of these two figures, where we have the current Arctic vegetation and here projected vegetation for 2090 to 2100. And you can basically see that these green areas are pushing towards the coastline, so a major shift in vegetation zones. Now, what is behind all these changes that we just saw? Of course, we are emitting quite a bit of carbon, and here is the curve that indicates how we increase our emissions. And then the second curve here, this brown one, shows the resulting CO2 concentrations in the atmosphere, because we are holding a lot of these emissions in the atmosphere. And then this curve shows the resulting changes in temperature. And here are the past 100 years or so, and you see that well-known wiggle in the temperatures towards a warmer world. And this is about worldwide about 0.6 to 0.8 degrees Celsius change. Wally has talked about it, so I will make this short here. We have, of course, seen in the past that the Earth went through different states, And if we are looking at this paleo record where we went from high to low temperatures, it was related to the way the ocean circulation worked, and specifically how far north the thermohaline circulation actually reached. And the further north it reached, the warmer it was, and vice versa. The way this works in a very simple cartoon is that if we have increased fresh water coming from the north, it can actually stratify this area over which the deep convection forms deep water, and as a consequence pulls water from low latitudes northward. If we decrease the flux of fresh water out of the Arctic, then we are taking that effect away, and we have a higher rate of convection and a higher rate of flow of this branch towards the north, with all the consequences on sea ice formation and temperature over the ocean and the adjacent land. So the key question then is, can changes in freshwater fluxes from the Arctic to the North Atlantic shut down the conveyor? And if so, what would be the consequences if we do that in a greenhouse world, meaning in a world that is significantly warmer than it was during the past glacial interglacial cycles? In order to look at that, we have to rely now heavily on model projections, and Wally already hinted at the fact that they have quite a bit of strength. They are also our only tool to look into the future, but they also still need quite a bit of work to get all the observations right. But if we are looking at the projections from the IPCC models, and here we are using the 2001 runs, which are done with realistic global warming, meaning with CO2 increase, then here we have the year 2004, basically close to the present. Here is the strength of this conveyor belt, and just at around now, according to many of these model simulations, here you see each color is a different model simulation by different groups. We are just at the point where we should start to see a slowdown of the conveyor belt. Now, if we would manage to basically stop the conveyor, then in a model-only simulation, the sea surface temperature should cool significantly over the North Atlantic and sort of reaching down into the mid and low latitudes in the Atlantic. And if we would reduce the deep water formation in the North Atlantic, then through the sea ice mechanism, we should actually expect cooling over most of the North Atlantic, and as we will see in a moment, also over the adjacent continent. The question really is, can we do that, and if so, would that also work in the future? Wally already gave you the answer, but we will go through that. In a publication that responded to the movie The Day After Tomorrow, researchers from Scandinavia concluded that there is a possibility that the North Atlantic thermohaline circulation, basically the conveyor belt, may weaken substantially during this century, and this would have unpleasant effects on our climate. Not a disaster-moving ice age, but perhaps a cooling over parts of northern Europe. The question is, would that really happen? So let's quickly look at the freshwater components and whether or not there is enough freshwater to really shut the conveyor down. If we are looking at the Arctic again and see how much freshwater it holds, we can see what the freshwater effect is from river runoff. And if we integrate the freshwater sitting on top of the water column up into a layer of pure freshwater, we have about 13 meters or so. So that is the capacity that the Arctic holds. If we are looking into the Pacific Ocean, into the Pacific sector of the Arctic, then we have pressure water coming into Bering Strait. That corresponds to about 40 meters of Pacific water, or 4 meters of pure fresh water. That would make about 17. Sea ice extracts fresh water and releases salt. That would take about 3.5 to 4 meters away. So we are left